Okay, good morning. This is Tim Stewart. I am president at Visual Decisions, and we are here today to talk about maximizing mean time between failures with Industry 4.0. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory and the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements such as 30% increases in OEE, 50% scrap reductions, and much more. But just like wearing a Fitbit won't automatically make you thin, implementing technology for Industry 4.0 won't automatically make the business better. The culture of the organization and the business processes have to be adapted to take advantage of the new capabilities to drive real improvements. This is why we have a unique approach to work with our customers to adapt those processes to take advantage of the new capabilities and to help establish a true data-driven manufacturing culture. So we're here today to talk about how companies maximize mean time between failure. We're going to get started with some looks at traditional and current approaches and so forth, and how those might be supplemented with Industry 4.0. Just a quick note, if you have questions, go ahead and enter those into the Q&A and I'll address them at the end of the talk. So how do companies keep equipment running today? What are the different practices that are used to prevent unplanned downtime? So overall today, I'll be talking about different ways to maximize the mean time between failures. MTBF is a simple concept. Just take the average length of time the machine can run without failing, and that's the mean time between failure. It is an incredibly useful measurement for how effectively I can run my equipment. An infinite MTBF would mean that the equipment will never fail again. So we definitely want to maximize it as much as we can. The devil, as always, lies in the details. You can look at the mean time between any failure, which is the calculation described above. That gives very useful information for how well the equipment is running and how much we can produce. I can also look at the mean time between same failures, which gives me an idea of the magnitude of the different types of problems for the machine. This metric is much more useful for measuring process improvement related to things that we've targeted at particular failure modes. So there are many different tools one can use to increase the time between failures. In this series of 3 webinars around mean time between failures, mean time to repair, and then first time fix rate, I'll be looking at some of these things in particular to how to make them more effective with Industry 4.0. It's not meant to be an exhaustive list, but it's a good start for a 30 to 40-minute webinar. So some of the maintenance practices that we'll look at are autonomous maintenance, preventive maintenance, condition-based, and predictive maintenance. And some of the other things that companies do to impact the mean time between failure and how effective the equipment is running and so forth are Kaizen and root cause analysis within those improvement events, and then failure mode and effects analysis. So how do we provide help to those, and what is the impact that Industry 4.0 can have? So some of the things that we'll look at, well, one of the primary tools for improving the mean time between failure is machine monitoring. To be clear, just collecting the data doesn't fix anything, as we talked about earlier, but the data is foundational to having success with any of the improvement programs I talked about. And just some quick examples. Understanding the impact of preventive maintenance activities to optimize when they're done, getting detailed tag or process variable information to use as the basis for condition-based maintenance, having data to feed into the machine learning process for predictive, targeting a Kaizen process, and having the data for root cause analysis. So if you have to start somewhere to improve the effectiveness of your maintenance program, start by using an I-IoT platform to collect the impactful data from your process. So what is I-IoT? The Industrial Internet of Things, or I-IoT, describes the network of different objects or things that are embedded with sensors, software, and other technologies for the purpose of connecting and exchanging data with other devices and systems over your network or over the internet. And so essentially, you're going to focus on the data collection, data routing and persistence, event processing, communication with alerts and things like that. They will always have development environments and mashup and user experience builders and so forth. Machine learning and AI systems are usually built into these, and they usually have a very highly extensible API so that you can configure them to match, pretty much any problem you're trying to solve within the organization. So that's what an IIoT system is. Augmented reality can be done with your phone. It can be done on a tablet. It can be done with the glasses that you wear and so forth. But it's an interactive experience on top of the real world environment so that you can see what's happening in the real world, but you can also see some information overlaid on top of that. And we'll be seeing several different examples of that today. And then artificial intelligence or machine learning are computer systems that are able to essentially forecast out what are the trends and how is that going to look in the future. And so they can start to look at what's happening in the machine right now and understand if that portends that the machine is going to have some sort of failure in the future. And so that's where that comes into play. So how do we go about maximizing the mean time between failure with the Industry 4.0 solutions? I'll start with autonomous maintenance. And one of the pillars of TPM, or total productive maintenance, is to have the operator take as much ownership of maintaining the machine as possible. It's sort of like doing your own basic maintenance on your car. It'll be more efficient from a cost perspective and probably done with more care and attention since you own the car. But a lot of people don't even change their own oil or even really their own wiper fluid. Other than being too busy, the biggest hurdles are that some combination of not knowing how, not having the equipment, or not having the consumable, the oil, the fluids, etc. And it's the same thing for the operators in their machines. They're measured on production, so they don't have the time. The equipment and the consumables aren't at the machine. They don't have instructions of what should be done and when. They're unsure when to perform which tasks. With Industry 4.0, all of those different issues can be addressed to some extent. The system will know how many pieces have been made since the previous activity, so the operator doesn't have to track that. The system can provide a list at any time of what activities have to be performed and step-by-step instructions on how to do it. Now, if I could only get those tools set up in my garage at home, it would be much easier to maintain my cars. So then, if we look at some of the tools that are out there for being able to do these things and assist operators with autonomous maintenance, we can look at a connected work cell. And with a connected work cell, I can provide information about tasks that need to be performed from an autonomous maintenance point of view. If the operator shows up at the machine in the morning, they have a list of things that they're supposed to address on the machine because the system knows where the machine is at and so forth. That can make the life of the operator much more simple. And then you can also provide the digital work instructions and so forth to be able to do those things. And if we look at those work instructions, they can be provided in many different ways. What I have found remarkably effective is to provide those with that augmented reality experience. So if you're looking at operators doing these tasks correctly and being able to transfer the knowledge from your maintenance team to the different operators that are out there on the floor, you don't necessarily have to use the glasses. You can use just a smartphone or a tablet or something like that. But having those instructions be virtualized so that you can kind of overlay the visual of what is supposed to be done right over the machine itself is incredibly effective for making sure that those things are done correctly in the first place and minimizing the amount of time that it takes to get them done. And so a lot less training, a lot faster time to value for an autonomous maintenance program as part of TPM. Just a lot of different advantages for this. From a preventive maintenance point of view, PM has been a staple of increasing machine reliability and OEE for decades. For such a well-established process, you might ask what Industry 4.0 can possibly do to improve it, and it's kind of a lot, actually. So a lot of different PM tasks are kind of reactive in nature. They get added when the machine fails in a particular way, and so now I'm going to put a PM task in place to make sure that that never happens again. Task frequency is often just kind of an educated guess without a lot of validation done to optimize that timing. The task efficacy is usually not studied to ensure it's preventing what it's supposed to, or whether it's needed in the first place. But using a system like I-IoT to collect data can help address all of the issues listed above, but it must be done with forethought and intention. We at Visual Decisions utilize a process to kind of list out each PM activity and identify elements from the machine for each task. And the key for PM is looking at the frequency of the different failure modes. And tracking that data can tell us, how effective are the PM tasks that are being performed. So if we still see those failures, even though we have the PMs in place, we understand that, we need to do something either more frequently or do something different. But we can also, experiment with the PM interval to see if that generates additional failures in the process and so forth, so that we can utilize this data to optimize which tasks are being performed and how frequently they're being performed over time. And using data that in that way helps to keep the machines running effectively while also minimizing those PM costs. So to help with this, obviously, we want to be able to monitor the process and understand when the machine is going down, why it's going down, and so forth. So being able to track those reason codes in addition to just the fact that it's up or down is very important there. Condition-based maintenance is similar to preventive maintenance, but instead of performing the preventive tasks at a set interval, what you're doing is you're looking for various conditions within the machine and utilizing that to set the timing of when those tasks need to be performed. And so the impacts of Industry 4.0 on condition-based maintenance are pretty straightforward, actually. Everything discussed with the preventive maintenance still applies, but now we're monitoring the tags or the process variables and setting tolerances on when we need to take action based on the changes in those tags. And this is where the real power of the I-IoT systems come in, the ability to collect and contextualize and analyze those detailed data streams. Analysis is performed to find which of the data streams are leading indicators for the different failure modes. And some examples of that are often temperature, vibration, power draw, et cetera. And once you find out which of those are indicative of coming problems, then you can create tasks around when those process variables show changes in the value, they go outside tolerances. You can both alert different people as well as then perform some PM activity based on that condition. And once again, I want to talk about augmented reality, so that once you do those tasks, you have those visual instructions right there with you as you're actually working through that process. So again, I-IoT is critical here. being able to connect to those machines, get that detailed process information, being able to, chart that out, be able to show that visually, but also be able to analyze that, set the tolerance bands. I have customers that are doing statistical process control rules, on those process variables coming off of the machine controller itself, so that they can see, when things are essentially getting, out of control, and utilize that for their condition-based maintenance. And you can set it up so that it utilizes all of the Western Electric rules, whether it's 2 data points out of 3 outside of 2 sigma, any point outside of 3 sigma, etc. So the next step is the one that's very popular these days, which is predictive maintenance. And if we take the next step to see how that same data can be used for predictive maintenance, essentially the frequency of each different failure mode now becomes the output that we're trying to predict. And so we need to capture the information about the different failure modes so that we can feed that into the model as the output variable that we're trying to correlate things to. And then the sensor data, the process variables that are coming from the either the sensors or the PLC and so forth, those are the data streams, the time series data that the learning model will be monitoring to make its predictions. And in this case, the model learns over time which of those different data streams are leading indicators for the different failure modes. And again, these are often elements such as temperature or vibration or power draw. And as the data flows into the system, the model is essentially performing pattern recognition to see how likely a failure is based on those recent history of inputs. So it's looking back in time. We've trained the model based on those process variables, how they transition over time, when the failures happened, and the software learns on its own what are the changes in those inputs that are predictive of those outputs. And so the key difference with the predictive versus the condition-based is the sophistication of that model. With the learning model, the algorithm can automatically determine which are the leading indicators, what to watch, and when to actually alert people that a failure is imminent. So with predictive maintenance, you have those same feeds coming from the system, but now you're feeding that information into that AI or machine learning model, and you're taking the outputs and you're hopefully utilizing those now to actually make those maintenance routines on the equipment happen. And so the advantage here is that essentially, in the past, you had various choices. You could either do PM activities, at a set interval, or you could look for, kind of big changes in the condition of the equipment, or you could basically just run until failure. And for some things, running until failure was actually the right choice because it didn't have any catastrophic things. It didn't cause long downtimes. And, it was something that you could just make a quick change and keep going. What the predictive allows you to do is basically treat most anything that you can accurately predict as a run to failure, except you're not quite running to failure. You're running to almost failure, and then making whatever change you need to make, and then restarting. And so it gives you essentially the optimum amount of runtime before you need to make some changes. Now, some of the other tools that I talked about, like Kaizen or root cause analysis and so forth, are also very heavily impacted by Industry 4.0. And while these aren't maintenance specific, they're definitely tools that companies utilize to say, what is causing the major, reasons for downtime on these different machines. And now let's organize an improvement project around fixing those things. And so with Kaizen, this is a very typical 6-step cycle for Kaizen. And what I do is I identify my problems, I analyze the current process, create solutions, test the different solutions, measure and analyze the results, and then standardize that across my different processes. And what we have found is that Industry 4.0 and having that data from the process and so forth improves each and every single one of these different steps. Whether it's identifying the problems that you have and understanding what are the key drivers of performance out on the shop floor, or doing the detailed analysis of the current process and so forth, all the way through the process, having that data is absolutely key to making those improvements and then sustaining them over time as well. When you look at actually doing the root cause analysis for those, whatever system you're using, whether it's something as kind of simple or basic as, who's running the process, what are they producing, when is it being run, when are the problems occurring, where in the equipment is it happening and so forth, or whether you're asking why 5 times and trying to drill down into the process and so forth, all the way through, running a statistical analysis of factors, doing an ANOVA, design of experiments, et cetera. Any one of those is very, very heavily dependent upon data. And the more data that you can have about the process, the better off you are. Now, one thing I'll say about that is, the right time to start collecting the data is, last year, so that you have 24/7 information about what was happening in the process, over the last 365 days. The next best time to start is right now, so that when you do have a problem in the future, you'll already have the data. And so there are a lot of different things that you can do to determine, which processes should I monitor in detail, what information from those processes I should collect and so forth. And please, reach out to me and we can have those discussions. Finally, kind of a word about FMEA. FMEA is a very, very powerful process, failure mode and effect analysis. It's been around since, I think it was the 50s. And, it goes through a very detailed process of identifying what are the different failure modes and what are the effects of that failure. So that tells you symptoms that you can look for. What are the potential causes or mechanisms of failure? So the root causes, of those different failure modes. And then, the key thing is understanding the severity of it. So when it happens, how long am I down for? Or, are there effects where this injures somebody, or, other things that, make it a more severe issue? Is it, something that happens frequently versus infrequently? So the probability of occurrence, and then also the probability of detection. And when you start to look at all of these different portions of an FMEA, what they really help you do is to understand, for your different failures, how frequently are they occurring and why are they occurring, and then what can be done about it, what are the recommended actions. And this obviously ties into your mean time between failure, and what are your different plans for making that increase over time. And so what we've done with our customers is to actually tie in the shop floor data collection with kind of a live FMEA, where we can see when the failure mode occurs, how big of an impact is it having on the process. And so that helps us determine the severity. When we look at the probability of occurrence, we can actually grab that information straight from the shop floor and be able to do that. The probability of detection is a little bit more tricky, but essentially what these systems do in terms of the impact on probability of detection is, when you think about being able to track those detailed process variables and so forth, if you can start to tie some of those things to where they either directly point you to that failure mode, or if you can set them up so that they can indirectly you can infer that you had this particular type of a failure from those. Now your probability of detection goes way up because of those different systems that you're putting in place and those different capabilities. So with that, thank you very much. If you do have questions, go ahead and enter those into the Q&A. I don't see any at this time, so I want to thank you all for attending. And if you do have questions, please reach out to me at tim@visualdecisions.com or my phone number there on the screen. And I do have one question. So after you have a solution, what mechanism do you have to track the change? Great question. So one of the advantages of putting these systems for data collection in place is not only do you have the information beforehand in order to make those changes, but you also have a way to kind of keep the light shining as you leave the room. And these tools can monitor, what that performance looks like. And if things degrade once, the engineering team, kind of finishes with their improvement event and, goes on to the next problem, these systems will detect that you have, a change in performance, and you can actually then, reinforce kind of the new disciplines from that change. And so that helps you, instill that new standard work around, how you should run the process in the future. Hopefully that answered your question. How do I validate that the data I am collecting is both sufficient and pertinent to understanding the system? Also a very good question. So you have basically conditions that are necessary and sufficient. And so, there are things that you're going to be monitoring that are absolutely necessary to be able to make predictions. And then you have to capture all of the different things that are required in order to have these sufficient things to accurately make predictions. And the way that you can validate that you have the right data is, first of all, that your predictions are accurate. But essentially, well, that is the biggest way that you're going to be able to tell over time. So happy to talk about that in more detail and kind of walk through that process in more detail than I can in a couple minutes answering questions in a webinar. But if you reach out to me, it's a good topic of conversation for more details. And you're welcome. Any other questions? All right, well, with that, thank you very much. And I will probably reach out to each of you to follow up a little bit and see what you're doing around maximizing MTBF in your companies. Thank you very much.